Hey gang, this will be the last video in our unit over radical functions, and in this video we'll look at how to graph square root functions. So if you think back to last semester when we looked at how to graph quadratic functions and parabolas, we talked a little bit about what are called parent functions and function families, and the parent function is just the most simple function you could have for a specific function family. So for quadratic functions, for instance, that was the function f of x equals x squared. Okay, so it's the most basic function that still qualifies as that function family. For square root functions, that would be f of x equals square root of, or radical x. Okay, so the first thing I want to do is show you what the parent function of this function family looks like, and we're going to fill out this table of values below. So if I pick the x values of 0, 1, 2, and 3, and 4, and I plug them in for x into this parent function, I get the following results. So the square root of 0 would just be 0. So that means this function would have a point at 0, 0. The square root of 1 is 1. The square root of 2 is not going to be a nice whole number. Okay, so I'm going to have to approximate with a decimal to get the square root of 2. And when you do square root of 2 on a calculator, it comes out to be approximately 1.4. Same thing with the square root of 3. It comes out to be approximately 1.7. And then we know the square root of 4 is 2. Okay, so if you go to plot those 5 points on the coordinate plane, especially the 3 whole number points, 0, 0, 1, 1, and 4, 2, okay, you would get this basic shape. It looks sort of like a sideways parabola, but notice it's only one-sided. Okay, so there's not another side to that, and there's a reason for that. Okay, so let's talk about the domain and the range of this function. So the domain values, again, those are all the x values, are all of the x values starting at 0, and this function goes to the right forever and ever, so it's actually all values that are greater than or equal to 0. The range of this function, similarly, is all y values greater than or equal to 0. Okay, this function keeps on going upwards forever, but notice there are no negative values for either x or y for this function. Well, let's think about that. The reason being is I can't plug, for this case, a negative x value underneath my square root sign, because then I would be taking the square root of a negative number. And the square roots of negative numbers, we know, are imaginary. We can't graph imaginary numbers on our coordinate plane. So because of that fact, okay, the domain and range for the parent function, in this case, is x and y are both greater than or equal to 0. Okay, we'll come back to domain and range here in a little bit. I want to talk about some transformation rules that will be helpful as you go to graph your square root functions. So these are similar to the transformation rules you learned for absolute value graphs and quadratic graphs. You just have to change your mode of thinking to square root graphs now. So if you have this alteration on the parent function, okay, y equals a times the square root of x minus h plus k, then the following will be true. A vertical translation will happen whenever you add outside of the square root sign. Okay, so if I'm adding a number outside the square root sign, for instance k, okay, that's going to shift the graph upwards. If I'm subtracting outside, that's going to shift it downwards. A horizontal translation will happen whenever I'm adding or subtracting inside the square root sign. So adding inside actually shifts the graph left, and then subtracting shifts it to the right. So again, it's the opposite of what you think based on the sign for the horizontal translations. A reflection happens whenever your radical term, in this case that a value, is a negative number, and so that flips the graph over the x-axis. So those are just some useful transformation rules to keep in mind when we're graphing. When we do our graphs, though, we're going to create a table of values, and so I'm going to show you how to do that on the back side here in a moment. There are two basic steps to that. Step 1 is to determine the minimum value of x. For all of these square root graphs, x is going to have a minimum value. For the parent function, the minimum value is 0. And after you determine that minimum value, then you're going to make a table of values starting with that minimum. So let's see how that works with example 1 on the back side. We have the square root function y equals square root of x minus 2 plus 5. Okay, so I'm going to create a table of values here. And the very first thing I want to determine is, what is my minimum x value? How small can x be? Well, let's look at what's underneath our radical. We have the expression x minus 2 underneath our radical for this problem. We know that whatever is underneath the radical, so the radicand, cannot be less than 0. So therefore, it has to be greater than or equal to 0. So for the parent function, we just had an x, so we said x was greater than or equal to 0. For this problem, x minus 2 has to be greater than or equal to 0. So therefore, if we just isolate x here, we know x has to be greater than or equal to 2. So that is my minimum x value. X cannot be below 2. From there, I can just pick more x values to plug in to my function and hopefully get some nice numbers. So I can pick positive 3. I can pick positive 4. I can pick positive 5, and I can pick positive 6. So you want to get at least 5 values in your table, okay? And I'm choosing 2, 3, 4, 5, and 6 for this one. Okay, so now when I go to plug these in, I'm plugging into this expression each time. So the square root of x minus 2, and then we're adding 5 at the end. So here, when I plug in a 2 for x, the square root of 2 minus 2 is 0. So this gives me 0 plus 5. So I will get a 5 for my y value. Here, when I plug in a 3 for x, I get the square root of 3 minus 2, which is 1. So I get the square root of 1 plus 5, which just becomes 1 plus 5, which is 6. Here, I get square root of 4 minus 2, which is just square root 2. Again, square root 2 is not a whole number, so you have to get a decimal answer for this one. If you do that on your calculator, again, the square root of 2 is approximately 1.4, and so we do 1.4 plus 5, and we get 6.4. Same thing for plugging in a 5. We end up getting the square root of 3 plus 5. The square root of 3 is approximately 1.7, so you get 1.7 plus 5, which is 6.7. And then finally, square root of 6, we end up getting square root 4 plus 5, which becomes 2 plus 5, which is 7. Okay, so when we go to graph this, we're going to graph our 3 nice points here, 2, 5, 3, 6, and 6, 7. So here's 2, 5. Here's 3, 6. And here's 6, 7. And we're going to keep in mind of what the shape of this is supposed to look like. It's supposed to look like a sort of sideways parabola, but only on one side. So it will look something like this. Okay? Keep in mind of where your starting point is. Okay, the directions also ask us to state what the domain and range are. So that's easiest to do once you get the graph down. So we know our domain has to be all x values that are greater than or equal to 2. Your domain is just from whatever you find your minimum x value to be. Your range, again, based on the graph, we see that the lowest y value is 5, so we can say that the range is all y values greater than or equal to 5. Okay, let's do the same thing for number 2. Number 2, this time we see that we have an a value there of negative 2, and because the a value is negative, we can expect a reflection for this graph. So we'll take a look at the end and see what the reflection looks like. Same process as before. I want to determine what my minimum x value has to be. So the expression underneath my radical is x plus 3. So I know x plus 3 has to be greater than or equal to 0. Therefore, x has to be greater than or equal to negative 3. So depending on the function, your x values can be negative. Okay, your x values can be negative. Your entire radicand cannot be negative itself. So we'll start with a negative 3. Then I can choose -2, -1, 0, 1. If I think ahead a little bit, I could also try to choose values that will make my radicand a perfect square. So I could choose 6 and plug it in to my function, because that will give me a 6 plus 3, 9. So you could even skip some of those values that will give you decimal answers and choose x values that will give you whole number answers, okay, assuming you can plot them on your coordinate plane. So now, we'll be doing this each time. We'll be taking the x value plus 3. So in this case, -3 plus 3 will be 0. So we have -2 times 0, which is 0, minus 1. So we get -1. Then we plug in a -2. So we get -2 times, we end up getting the square root of -2 plus 3. So the square root of 1, which is 1. -2 times 1 is -2, minus 1 is -3 here. I'm going to go ahead and skip -1 and 0 because I know those will give me decimal answers. I'm going to skip down to +1. And if I plug in a +1, I end up getting -2 times the square root of 4, which would be -2 times 2. -2 times 2 is -4 minus 1 is -5. And then I'm going to plug in this +6 here at the bottom. And again, I chose 6 because I know 6 plus 3 will give me a 9 underneath my square root. So I end up getting -2 times the square root of 9, which is 3 minus 1, and this becomes -7. Okay, so 4 points is enough to plot this. Even though we could go and do -1, 0 and get our decimal values, if we have 4 points, we could go ahead and get a good shape for our graph here. So -3, -1 would be our starting point. -2, -3, our next point. 1, -5 is here, and then 6, -7. Is here. So this graph, you can see, curves down this way. And if you think about, again, flipping the parent function over the x-axis, then that's what a reflection over the x-axis would look like. Okay? This will change, okay, this will change our domain and range values slightly. Well, your domain actually will be the same as the last one. So our minimum x value was -3, so same here, your x values have to be greater than or equal to -3. This time, though, our range, instead of having a minimum range value, we have a maximum range value. The highest point on this graph is -1, so we would say that the range is all y values that are less than or equal to -1. Okay, lastly, for number 3, we have an inequality. We have y is less than square root of x minus 4 minus 6. So we'll do this the same way as we do regular equations, except for inequalities. Remember, when we graph those, we have to watch the boundary lines or curves, and we also have to do some shading at the end. So my minimum x value for this graph is going to be x is greater than or equal to +4. We know x minus 4 has to be greater than or equal to 0. So we'll start with a 4 here. I can plug in a 4, I can plug in a 5. I can also skip ahead and plug in an 8 for x. And those will give me some nice numbers underneath my square root sign. So if I go and plug in each of these numbers for x, plugging in 4, I end up getting 0 minus 6, so -6. Plugging in 5, I get 1 minus 6, so -5. And plugging in 8, I get the square root of 4, which is 2, minus 6, which becomes -4. So I end up plotting the points 4, -6, 5, -5, and 8, -4. So the shape of my graph is going to be the same way as number 1 was, but when I connect my dots, I have to remember that a less than, okay, or a greater than, I'm going to use dashed as opposed to solids to create my curve. So my curve will look like that. And then my shading, it says y is less than x minus 4 minus 6. So I'm going to shade all of the y values that are below this curve. So I'm going to shade all of these values here. Okay, when I go to list my domain and my range, okay, your domain is still the same as what we did before. It's all x values greater than or equal to 4. Okay, and then your range for this graph, okay, you have to be careful on this one. Even though we're tempted to say that the minimum range value is -6, this is an inequality. Okay, so really, because we're shaded underneath the graph, okay, and we're including all the y values underneath, there is no minimum range value. This graph is also forever increasing, so there's also no maximum range value. So we could say the range of this inequality is all reals. And that's, again, because of the shading beneath the curve. Okay, any questions over this video, be sure to jot those down, and we'll address those when I see you next. Until then, have a nice day. You're all wonderful people. Take care.